I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, I'm going to discuss a few numericals that are based on de Broglie's concept or de Broglie wavelength. And since this is the first lecture I'm going to deliver on numericals, I would like to highlight the importance of numericals in physics. So numericals are basically physics problems. Whenever I call numericals or say numericals, they are nothing but problems in physics. There will be a problem statement given where you will have to solve it. So they are nothing but physics problems. And numericals play an important role while understanding the concepts. So why we do numericals is to understand the concept very clearly. So if you are able to do the numericals based on a given concept, means your understanding of the concept is very clear. Each and every physics law, equation or formula, each and every physics law, equation, formula have different aspects that can only be understood by solving as many problems as possible. So, if you have to understand different aspects of a physics law or different parameters, or you need to understand the equations. So, as you solve a number of problems, the different aspects of that particular law or the concept becomes very clear for you. So to understand the subject, you should be well versed with the important concepts and formulae related to the subject. And when it comes to theory, theory is very easy to understand. That is what all students feel. But when you get to numericals, then things look little painful. But that is only in the beginning. In the beginning, you may find it difficult to do the numericals because the application part, whatever you have studied in the theory or learnt in the concept, you should be able to apply it here in the numerical and be able to solve it. So in the beginning, you may find it a little bit difficult to understand or do, but later on as you practice, it becomes easy. Now, two factors that can help you to make a better physics problem solver. First, you should understand the principles of physics. So, unless you understand the principle or you know the formulae, you cannot solve the numericals. And the second thing is, you should have a strategy for applying these principles to new situations. You should develop a strategy. So, when you do numericals, you are learning all these skills. You will understand first what is given, what is asked, what you have to find out. And the second thing is you will develop your own strategy, your own method for applying the principles to new situations. Now, the ability to apply broad physical principles, usually represented by equations, is a powerful form of knowledge. Why I'm saying powerful is, it is more powerful than memorizing a list of facts. If you memorize, you may be able to apply it only for that particular problem or for that particular situation. But when a new problem arises or a new concept comes, how do you relate them or how do you apply them? It becomes very difficult. So if your basic concepts or the physics principles are very clear, so you will have a powerful form of knowledge and that you can apply it in any and every situation. So what is the approach we are going to follow for doing the numericals? So we'll use a general approach to follow each problem that we encounter. There are some standard steps we follow. Even though the strategy we use may be different, okay, we use different tools or tactics with different areas of physics, but the overall strategy remains the same. Most likely you have already acquired some problem solving skills because you are in the engineering, you have come to engineering and the first year level, you have already acquired some problem solving skills because you have done many numericals when you were studying physics at the intermediate level. And you also must have developed some habits. What were the habits? You know. No, you must have memorized things, or without understanding the concepts, you have just applied the formula and got the result, whatever it is. If you have got the right way, it is very good. Otherwise, what you need to do, like other areas of learning and life, some of the habits may be beneficial, but some may hinder your progress. Hope you understand what I'm talking about. Whatever methods or the problem solving skills you have developed or the habits you have developed may help you if they are in the right way. They may be beneficial, but if you have used the wrong methods, they may hinder your progress here, hinder your progress in learning how to solve physics problems. Okay, so it is for you to understand, learn or unlearn some of the things and move ahead. Now, many students say, I understand the material, but I just can't do the problems. No, in my career, I have seen many students talking about, I understand the theory, I can write all the answers correctly. But when it comes to numericals, I find it difficult to solve them. And if this is true for you also, okay, as a physics students, then you may have to develop your problem solving skills. You need to develop these skills, which is not very difficult. You only have to have your own strategy. And undoubtedly, the best way to improve your skills or the problem solving skills is practice. Okay. No, there is no other better way than practice. So you do as many numericals as possible. So you will become a master in it. Now, what is the strategy we are following? I told you we use a general approach to solve the numericals. The strategy we are going to use here is a 5-step strategy. First, you will understand the problem. Whatever problem statement is given, numerical is given, first you will have to understand. So then you recall the concept of the formula. What is the concept to which this formula is related? The concepts in physics to which this problem is related. So depending upon what is given, what is the formula you will apply, you will have to plan a solution. Okay. So suppose I'll give you a simplest example. You all know Ohm's law. Suppose you are solving the simplest one I'm giving you. You all know Ohm's law. What Ohm's law says? The ratio of voltage to current is always a constant, which is R. Suppose you are given a numerical in which the resistance is given and the voltage are given. Voltage is also, these two are given values, given quantities, and you have to find I. So identifying this from the problem statement is the first important step. So if you have to find I, you will have to simply rearrange the terms. That is how you will plan the solution. I know V, I know R. I have to find I. So what will be the formula for I now? I will be equal to V upon R. So simply substitute the value of V and R. Okay, that is what we call execute the plan and then evaluate the solution. So you will get the solution. Then other aspects are also there which we will discuss here. So, but this is the general approach. Understand the concept, the problem first. You will recall the concept on which it is based, plan a solution. You will execute your plan and then evaluate the solution. Now, some general rules that you have to follow while solving the physics numericals. We should have the same system of units for all the variables in the numericals. Whatever variables you have in the numericals, you should use the same system of units. When I talk about the system of units, we have different systems. The CGS, where we have the length in centimeters, the mass in grams, and time in seconds. So these are the three fundamental quantities we are talking: length, mass and time. It is in centimeter, gram and second. Now, if I follow the SI system, usually we'll be using the SI system, or in some cases it's also called the MK system. Length will be measured in meter, grams, mass will be measured in kilogram and time is in seconds. So mostly we'll be using the two systems. So if the data, all the data is given in the CGS system, that is centimeter, gram, second, you can as well continue in doing in CGS system. There is no problem absolutely. If all of them are given in the SI system, mass, kilogram and second, you can continue doing it in the SI system. But if there is a mix, if the length is given in centimeter and the mass is given in kilogram, then you need to convert this distance, which is in centimeters, to meter. Okay, you will have to do the conversion first and then only you can proceed. So you should ensure that the same system of units for all the variables in the numerical. I hope this is clear with this example. And the dimensions of the analytical expression should always be correct. So means when I'm talking about dimensions, I'll give you one more example. The equation, when it comes to equation, I'll take the first law of motion. Now, equations of motion we talk. V is equal to u plus at, where we say v is the final velocity, u is the initial velocity, a is the acceleration and t is the time. So whatever dimensions you have here, v, you also should have the same dimensions and at also should have the same dimensions. If you are writing just a or just t, it is wrong. You understood? So this you may not encounter in many things, only in cases where you are getting equations. You should also take care that the equations you are using are dimensionally correct. Then, if a correct diagram of the problem is drawn, it helps to understand the scenario of the numerical very easily. But in some cases, it is very much required, especially when you are dealing with forces. Now, I say an object of mass m is placed here. Now, if I have to talk about how is its weight or the force or due to this mass acting, so then I'll have to draw. So mg always acts vertically downward. Understood? So in some cases where you may have to, suppose you have an object on an inclined plane. Okay, this is the plane. You are keeping an object of mass m. Now, how is the mass of this object acting? It is also acting always vertically downwards. Now, then you may have to resolve it into two components like this. Or unless you draw simple diagrams to understand the problem, it will be very difficult. And once you draw it, it becomes very easy to solve the numerical. Now, before going into the numericals, we are going to solve some numericals based on de Broglie wavelength. So before we solve the numericals, we'll have a quick recap of the formulae that we are going to use now. So the first one is lambda is equal to h upon p. Okay. So I'll write the constant because we will be using it again and again. Lambda is the wavelength or the de Broglie wavelength. H is the Planck's constant. P is the momentum. Okay. And suppose if the momentum is not given, the velocity is given, we will use h upon mv. So here m is what? M is the mass of the particle. M is mass of particle. And v is velocity of particle. Okay. Then if velocity is not given, you know the energy of the particle, then you will use the formula lambda is equal to h upon under root 2me. So lambda h m we have already mentioned. So what E is here is the energy or the kinetic energy. It is the energy of the particle is given. So we'll use this formula. And if the voltage applied is given, the energy is due to the potential that is applied, the electrons are accelerated with a given potential, then you will be using the formula lambda is equal to h under root 2m EV, because capital E is equal to EV. So what is small e here? Capital E is the energy. Small e here is the charge of particle. If it is an electron, the charge of the electron. If it is a proton, the charge of the proton. And capital V is the potential that is applied. Okay. And sometimes you may also be asked directly to find the kinetic energy of the particles. So if you know the velocity, you can directly use half mv square, or after finding v, you can use ke is equal to half mv square to calculate. So all the things are known, and along with this formula, you also need to know certain constants. First thing you should know here is the Planck's constant. Now, in most of the numericals, the constants will be given, but otherwise, at your level in engineering, this will be very handy for you if you can remember certain constants. So H is equal to 6.625 into 10 power minus 34 joule seconds, H value, and then mass of the electron. If I'm talking about the mass of the electron, it is 9.1 into 10 power minus 31 kilogram is the mass of electron. If it is a proton, the mass of the proton is 1.67 into 10 to the power of minus 27 kilograms. Mass of the electron, mass of the proton. Then charge of the electron, E, 1.6 into 10 to the power of minus 19 coulombs is the charge. So for electron, it is negative, for proton positive, otherwise it is the same. We may not show the charge here. Okay, I think these constants are enough. And one more thing is the velocity of light, because sometimes we consider the particles moving with the velocity of light. So the velocity of light C is 3 into 10 power 8 meter per second. So all these things are required. The numericals are very simple, just to understand one simple concept, that is the de Broglie concept or the de Broglie wavelength. But you will be doing a number of numericals to make your concept very clear. So the first numerical is calculate the de Broglie wavelength associated with a proton moving with a velocity of 1/10 of the velocity of light. The mass of the proton is given here, 1.67 into 10 power minus 27 kg. So now, as I told you, whenever we are doing the numerical, you should first understand the problem, what is given. Okay. Then you will recall the concept on which it is based. After recalling the concept, you will plan the solution. Then you will execute it and then evaluate the answer. Okay. So how we are going to do it? First, write the data given. What is given here? It is moving. The proton is moving with a velocity given by 1/10 of the velocity of light. So data given is 1/10 of c. Okay. And the mass of the proton is also given, because we are talking about proton, you need to know the mass of the proton. So what is the mass of the proton? 1.67 into 10 power minus 27. And you also need to know the velocity of light, because here it is, velocity is not given directly. It is given as 1/10 of c. So obviously you should know what is the value of c. Okay. Then the formula which you are going to use is lambda is equal to h upon mv, because you know m, you know v. H is a constant. What is the value of h we are going to use? 6.625 into 10 power minus 34 joule seconds. We will use to get the value of. So we have substituted the value of h, 6.625 into 10 power minus 34. We have substituted the mass, 1.67 into 10 power minus 27. Here we have to write the velocity. How do you get the velocity? Very simple. It is given v is equal to 1/10 of c. C is the velocity of light. We have written the velocity of light here as 3 into 10 power 8. So 1/10 into 3 into 10 power 8 will give us 3 into 10 power 7. So the velocity is 3 into 10 power 7 meters per second. So we are going to substitute directly the value of V. Okay. So when you simplify, you can use your calci, and in fact, you need to use your calci and practice. Only then you will be able to use it in your examinations while doing. Okay, instead of simply writing the answer, you should use your calculator and know all the functions in the calculator so that you can solve problems very easily. So one method is you can keep all these numbers and the powers aside and do it separately, or using your calculator, you can use it directly. So the wavelength is given as 1.322 into 10 power minus 14 meter. Because we are using the SI system here, mass is given in kilogram, the velocity is given in meter per second. So definitely the wavelength is also in SI system, that is in meter. So what is the answer? The result is lambda is equal to 1.322 into 10 power minus 14 meter. Now coming to the second one. Calculate the de Broglie wavelength of an electron which has been accelerated from rest on application of potential of 400 volts. So what is given here? Potential is given. And what we have to calculate? We have to calculate wavelength. Wavelength of what? Electron. So it is very important to identify this first and then write. So the data given here is V is equal to 400 volts. So which formula do we use here now? We can directly use lambda is equal to 12.26 upon root V, because it is an electron and we have already derived. So this is coming from lambda is equal to h upon under root 2m e v. I told you h is a constant, 2 is a constant, m is constant, e is constant. When you substitute all these values, I can write lambda is equal to h upon under root 2me. I can solve the whole thing and write it as like this. So we have already solved this value in theory. It is coming out to 12.26 angstrom. 1 angstrom is 10 power minus 10 meters. So I am directly writing for this value, I have written 12.26 angstrom and we have root V. So it is the direct formula that we are using here. Lambda is equal to 12.26 under root V angstrom. So it is now very simple. 12.26 for V, what we are substituting? 400, which is given. 400 volts is given, so we substitute 400. So under root 400 is 20. So it is 12.26 by 20, which gives us 0.613 angstrom. Angstrom here is nothing but 1 angstrom is equal to 10 to the power of minus 10 meter. You can also express it in meter, no doubt, no problem about that. Otherwise, because you have this value in angstrom, you will also express them in this in angstrom. Now the next one. If the kinetic energy of a neutron is 0.025 electron volt. No, we will consider it as proton because we know the mass of the given is proton, so we will consider it as proton. Okay. If the kinetic energy of the proton is 0.025 electron volt, calculate the de Broglie wavelength. So what is the mass of the proton? 1.674 into 10 power minus 27 kg. And data given, you are given only the kinetic energy. 0.025 electron volt. Here you also have to do one more conversion because the energy is given in electron volt. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Okay, so I can convert this electron volts to joules by multiplying it with 1.6 into 10 power minus 19. So I've got the energy in joules. Now what is the formula we'll use? Lambda is equal to h under root 2me. E here is the energy which is given by 0.025 into 1.6 into 10 power minus 19. Let us do the substitution now. So the value, the constant value for h is 6.625 into 10 power minus 34 under root 2 into 1.674 into 10 power minus 27. We are getting it from the mass of the proton that is given into 0.025 into 1.6 into this is the energy. Okay. So you get the answer. You can simplify this and get the answer. Now the next one is calculate de Broglie wavelength associated with an electron raised to a potential of 1600 volt. So it's very simple. What is the data given? Only the voltage is given. The voltage is 1600 volts. And the formula you are going to use is again lambda is equal to 12.26 upon root V, that is the voltage in angstroms. So 12.26 under root V is 12.26 by 1600. Under root 1600 will give you 40. So 12.26 upon 40 is 0.3065. You can use your calci and get the answer, and this is in angstrom. If you want, you can also express it in meters as 0.3065 into 10 power minus 10 meter. So this is the wavelength associated with the electron which is raised to a voltage of 1600 volt. Now the next one. Electrons are accelerated by 344 volts and are reflected by a crystal, and the first reflection maximum occurs when the glancing angle is 60. You have to determine the spacing of the crystal. What you have to find is the spacing. So let us write the data given. What is the data given? It is accelerated by 344 volts. So V here is 344 volts. Okay, and the glancing angle is 60 degree. So theta is equal to 60 degree. And we are talking about first reflection maximum. First reflection maximum. So we have to take n is equal to 1. So in the first step, what we are going to do is to calculate the value of lambda. That is the wavelength of these electrons that are accelerated. So we'll use the formula lambda is equal to 12.26 under root V in angstrom. So 12.26 under root 344 because the voltage is given as 344 volts. So under root 344. So you will get it as 0.661 into 10 to the power of minus 10 meters. So here we have written it in terms of meter. Okay. Now, in order to calculate the spacing, we'll use the Bragg's law. This is the Bragg's law. What is Bragg's law? 2d sine theta is equal to n lambda or D will be equal to, if you take 2 and sine theta the other side, you get D is equal to n lambda upon 2 sine theta. Means we are writing what is required in terms of known values. N is equal to 1 we know. Lambda we have found out just now. And theta is given 60 degree. So we are writing it in terms of known values. So D is equal to n lambda upon 2 sine theta we are going to use. So anyhow n is 1. So n is 1 into lambda, the value that we have got just now, 0.661 into 10 power minus 10 divided by 2 sine 60. So you can substitute the value of sine 60 or get the value using calci and substitute. You get 0.3816 into 10 to the power of minus 10 meter. So everything is in the SI system. So we are going to express this also in SI. But if you have to write it in angstrom also, you can write it as 0.3816 angstrom. So the spacing between the crystal lattice is 0.3816 angstrom. Next one, calculate the velocity and kinetic energy of an electron of wavelength 1.36 into 10 power minus 10 meter. So what we will do here now is, in the solution, first you have to write the data given. What is the data given here? Wavelength is given. So lambda is equal to 1.36 into 10 power minus 10 meter. Okay. And we have to calculate the velocity and kinetic energy of electron. So you need to know the mass of the electron also. So the mass of the electron is 9.1 into 10 power minus 31 kilogram. Okay. So if this is the data you know, and you also have to use the Planck's constant, H is equal to 6.625 into 10 power minus 34 joule second. Everything in the SI system. Okay. So once you have the data, what is the formula we are going to use? We know lambda is equal to H upon mv. But you have to find V. So this implies V is equal to H upon m lambda. So substitute the values. 6.625 into 10 power minus 34 upon the mass is 9.1 into 10 power minus 31 into lambda value which is given 1.36 into 10 power minus 10. So if you substitute and use the calculator to solve this, you get 53.5 into 10 power 5 meter per second. So this is the velocity of the electrons. Now the next step what they are asking you is to find the kinetic energy. So what is the formula we are going to use for kinetic energy? Kinetic energy is equal to half mv square. So this is half m. And again we use the mass of the electron, 10 power minus 31 into v square. What is the value of v? We got 53.5 into 10 to the power of 5 whole square. So substitute and simplify, you get 1.304 into 10 to the power of 17 joules. So the kinetic energy is always expressed in joules. Suppose in the numerical, if they are asking you express the kinetic energy in electron volt, then what you need to do here is you divide this, because we'll use the conversion. What is the conversion? 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So we'll use the conversion and divide it with 1.6 into 10 power minus 19. And you will get the answer in electron volt. Okay. So this is how you will have to convert it into electron volt. Next one. Find the de Broglie wavelength associated with a 46-gram golf ball with velocity 36 meter per second. And the second one, an electron with a velocity of 10 power 7 meter per second. And then you also have to evaluate which of these two balls show wave character and why. So after calculating, you will have to answer whether they show the wave character and why. Okay. So first we'll write the data given. We will have to calculate the wavelength for the golf ball as well as electron. Now we need to compare. So we need to compare the wavelengths of the golf ball as well as electron. So for the golf ball, what is given here is the mass is 46 gram and the velocity is 36 meter per second. And for electron, the mass is not given, but we know the mass of the electron 9.1 into 10 power minus 31 kilogram. And the velocity is 10 power 7 meter per second. Now, if you observe, this is an SI system, this is an SI, this is an SI, but 46 grams, this is in CGS. So I told you, before you proceed to solve the numerical, you will have to check whether all the quantities given are in the same system or not. So if it is not, you will have to convert. So we will convert it into SI system. So that will be 46 into 10 to the power of minus 3 kilograms. Okay. So once you have written this mass, what is the formula we are going to use to calculate the wavelength? Lambda is equal to H upon mv. So lambda here will be equal to H is a constant 6.625 into 10 power minus 34 upon 46 into 10 power minus 3. This is in kilograms into V. V is 36. So you will get the answer as 4 into 10 power minus 34 meter. Okay. Now for electron, again lambda is equal to 6.625 into 10 power minus 34 upon 9.1 into 10 power minus 31 into 10 power 7. So lambda is equal to 7.3 into 10 power minus 11. So now we have got the wavelengths of the golf ball as well as electron. We need to compare which of these two balls show wave character. So you have to recall the concept. What is the concept here is, if you are getting the wavelength, if the wavelength is comparable to the size of the object, then only you will be able to see the wave character. That is the concept behind the wave nature. Because we have seen when de Broglie has given, it can be applied to microscopic as well as macroscopic objects. But only in case the wavelength matches with the size of the object, you will be able to see their behavior or see the wave nature. Now 10 power minus 34 is too small value when you compare with the size of the golf ball. And here if you see, lambda is 7.3 into 10 power minus 11, and when you compare with the size of the electron, which is of the order of 10 power minus 10 meter, then they are comparably nearly equal. So only an electron alone exhibits wave character. Okay, you should give the reason why electron is exhibiting the wave character. Whereas here It does not exhibit wave character. Why it exhibits? Because they have asked why. Why does it exhibit wave character? Because the wavelength is comparable to the size of the atom. So, size comparable to wavelength. So, that is why this exhibits wavelength. Okay, hope this is clear. Next, calculate the de Broglie wavelength of de Broglie waves associated with a proton of kinetic energy 500 electron volt. Okay, so we need to find what again? Calculate the de Broglie wavelength. Of what? Of a proton. What is given? Kinetic energy is given. So let us write the data given. Energy or kinetic energy 500 electron volt. That is given. And you need to know the mass of the proton. Mass of the proton is 1.67 into 10 power minus 27 kilograms. And what you have to find is lambda. What is the formula we are going to use? If energy is given, so we'll use the formula lambda is equal to h under root 2me. H is a constant, m you know, e you know. You can substitute. But before proceeding, what you need to do, you will have to convert this 500 electron volt to joules, because in SI system, energy is expressed in joules. So the energy will be equal to 500 into the conversion. 1 electron volt is 1.6 into 10 to the power of minus 19 joules. So 1.6 into 9, I will get 90. 900 into 10 power minus 9 joules. Okay, so now let us substitute these values here for lambda. H is a constant, Planck's constant, 6.625 into 10 to the power of minus 34 under root 2. Mass of the proton, we have already taken the mass of the proton as 10 power minus 27 into E. E in joules. So this will be 900 into 10 power minus 19. Sorry. So when you simplify it, you get 1.28 into 10 power minus 12 meter. So the wavelength is 1.28 into 10 power minus 12 meter. Next, calculate the kinetic energy of a moving electron which has wavelength of 4.8 picometers. So here there is one more unit that is given, 4.8 picometer. So let us write the data given. Lambda is equal to 4.8 picometer. So here again you need to know the conversion. 1 picometer is equal to 10 power minus 12 meters. 1 picometer is 10 power minus 12 meter. So I will convert it and keep it. 4.8 into 10 power minus 12. We are writing it in the SI system. Now you will have to find the kinetic energy of a moving electron. So definitely you need the mass of the electron. 9.1 into 10 power minus 31 kilogram is the mass of the electron. Now, K. So to calculate Ke, we will find V, because that is the, you may use any strategy. Okay. So here, because you know lambda is equal to H upon mv, so this implies V is equal to H upon m lambda. So substitute the value of H, 6.625 into 10 power minus 34 upon mass 9.1 into 10 power minus 31 into the value of lambda, which we have converted from picometer to meter, 4.8 into 10 power minus 12. So what do you get? The velocity is 0.15 into 10 to the power of 9 meter per second. This is the velocity we are getting. So once you get the velocity, you can find the kinetic energy very easily. So kinetic energy is equal to half mv square. So half m is 9.1 into 10 power minus 31 into v square is 0.15 into 10 to the power of 9 square. Half mv square. So if you solve it, what you get here is 0.102. You get 0.102 into 10 power minus 30. This is in joules. If you have to convert it into electron volt, again you will divide it with 1.6 into 10 power minus 90. So the answer will be 0.06 into 10 power 6 electron. So the kinetic energy in electron volts is given by 0.06 into 10 power 6. So with this, I conclude my session on numericals. What I suggest you is to take as many numericals as possible with different data and solve them by applying the problems or using your own strategy. That helps you to make your concepts clear and understand better. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.